So we're talking about shooting particles. Oh my goodness. Wait a minute. We recognize this. This is a particle that's about to get deflected by two charged plates. But what you don't realize is that the first two plates are vertical. And what we just talked about was the fact that if we could figure out what the difference in electric potential energy is across those plates for a charge moving from one side of the plate to the other, so across a voltage, that would be able to tell us how much kinetic energy that particle would have as it gets to the other side of those plates. And so what I did was I poked a hole, just a little hole in these plates. So honestly, this is a sheet of metal, and I poked a hole in it like that. Okay, I know we're seeing it in profile view here, so it just looks like there's a gap there. But that means that this charge is going to get sent across this gap. So let's just call it a Q. Let's call it a charge, Q. And we're going to say that it starts off with a speed of V1. And it's going to get shot out of, we could call it a particle cannon or something like that. But there's a little note over here that we've got cathodes are positive and cations are positive and anions are negative. And the little cat and onion picture reminds me of which one's a cation and an anion. But anyways, people have this device called a cathode ray tube, and a cathode ray tube, cathode ray tube fires electrons. That's what a cathode ray tube does. This is actually the old style tube television, like from the 1950s or more recently the 1990s. But that's what a tube television was. It was an electron firing gun. And these electron firing guns, here's a cross section of a cathode ray tube, they would shoot electrons, and using charged metal plates and magnetic fields, you could steer where the electrons would go. And those electrons would hit the entire interior of a screen, like say at that point right there, and it would make that point on the screen glow. Because the electron would boom, like hit the screen. It would hit right on a pixel and make that pixel glow. And you imagine you can use these positive and negative charged plates, and you could change the charge intensities on them, and you could steer the electron to woo, land on a place on the screen there, and you could make that part glow. And in fact, what it could do was it could do that almost like a dot matrix printer, and it could go and you could fire electrons all the way across the screen, like scanning the screen, and you could two-dimensionally, everybody's thinking about three-dimensional printers, two-dimensionally print an image by shooting electrons at a glowing screen. Now there's phosphorescence on the inside of the screen, so when the electron smacks into it, it glows at that point. And you could steer these electrons so well that you could get the blue portion or the red portion or the green portion of a pixel to glow, and that would make the full color palette for color television. You're like, what? They did this in the 1950s? Yes. So what we're talking about right now, remember, the earlier stuff, we only just discovered the electron in the 1890s. 1907, Millikan discovers the quantized energy of the electron. By the 1950s, happy days. We're watching color television. Like, wow, that's rapid technology progression. By the way, in the backdrop, just for fun, while they were figuring out how the telecommunications world was going to get revolutionized, they decided to have World War I and World War II. Dang, amazing. People do great things even when the background is messy. And that impresses me, right? Like, I think we should all be impressed that so many huge developments are happening in this neighborhood of history. Anyway, some awful things too, but some kind of like neat world-changing things in terms of technology and communications. I mean, the fact that we were able to televise colored television also meant that we could broadcast in living color the atrocities of war and get people's attention and maybe even drive people towards peace. Like there's some cool politics playing out here. Let's get at the physics though. I'm getting too political. We could measure the voltage across those two plates. And if we knew what the voltage was across those two plates, we could figure out, remember that's measuring the delta V value. Delta V, not to be confused with speed, okay? But if I could measure that delta V, and I recognize that this is an electron gun, that means that based on our previous conversation, we could figure out what the speed's going to be. Let's call it V2, as this electron fires out the other side of this plate. I'm calling it an acceleration plate because this is getting the electron up to speed as it's fired out of a cathode ray gun. Okay, an old-time TV. But this is honestly also an early particle accelerator, right? Not like the ones we have today, not like the Large Hadron Collider, but this is a little mini particle accelerator, an electron specifically. Now, this is a negative electron, of course. It comes out over here, and you guys can tell me what direction is this electron going to get deflected, upwards or downwards? Yeah, down. Yeah, it's getting repelled by the negatives. It's getting attracted to the positives. If I did want to put electric fields in here, I've said previously that negative charges get attracted against electric field orientations. So yeah, any way you think about it, this thing is going to get deflected downwards. And so we got this parabolic curve deflecting downwards. Now here's the next thing. If you really want to steer electrons to print a full two-dimensional picture, you don't want to just steer electrons upwards or downwards in the in the y direction. You'd like to be able to steer these electrons into the page and out of the page, like in the z-axis, right? And so here I've got two metal plates, and I'm trying to make them three-dimensional. I've taken a negative plate and I put it in the foreground, and a positive plate and I put it in the background. Can you guys see what I'm talking about there? Almost like two sheets of paper, but they're metal. That means that this electron is going to get what? Steered towards the front plate or away from the front plate? Away from, into the page, right? So it's hard for me to draw three-dimensionally on a two-dimensional surface. So I'm just going to say, yeah, it gets steered into the page. And the way that I'm going to represent that it got steered into the page is, here's the screen that I'm shooting it at. This is the inside of a television screen, an old-time television screen. And this electron just landed right there on the edge of the screen, the inside of the screen that's furthest from us in the bottom corner. You guys picking up all this three-dimensional stuff? We don't do a lot of three-dimensional stuff. But if you want to print a two-dimensional TV screen, you have to be a three-dimensional, kind of high-level thinker. This is really impressive that they did this thing and mass-produced it and sent pictures. And it was entertaining. Right? Like, this is, I think, cool. All right, so with all that said, this is by the way, there actually is some more control here using magnetic fields. I'm really just doing the basics, okay? This is just electric field steering. There's magnetic field steering as well. So if you ever open up an old tube TV, like if you find a busted antique one or something, you'll see some magnetic coils as well. You absolutely will. And I have a broken one on a shelf here in the classroom. I can show it to you later if you want to. It's from a mini TV that somebody donated to me once upon a time. Well, maybe I threw it away because it had some sharp glass edges. I'll look for it. Anyway, an electron with a mass of 9.1 times 10 to the power of negative 31 kilograms. And can I get everybody to just say, boy, that's small? 3, 2, 1. Boy, that's small. Yeah. And a charge of 1.60 times 10 to the power of negative 19 coulombs. Can I get everybody to repeat after me? Boy, that's tiny. 3, 2, 1. Boy, that's tiny. Yeah, right? So these are small, and small matters. This is a small mass and a small charge, but that's okay because electric force is what? Big. Yeah, it's going to do stuff. All right, so this charge has a mass, and it has a Q value. And it's introduced into a pair of acceleration plates. Remember, that's the first pair of plates at an initial velocity of 0 meters per second. Now, we're just going to say, oh, this electron just barely ionizes away, right? Remember, cations, anions, okay? Just barely ionizes away, so it gets introduced with the speed of 0 meters per second. And the acceleration plates have a potential difference of, oh my gosh, 3 times 10 to the power of 4 volts. Can you guys say for a second that that's big? 3, 2, 1. Yeah, that is big. That's 30,000 volts. That's not a television. This is something at like a big laboratory or something, right? So this is a high voltage television, if anything, but it's a particle accelerator. So find the exit speed from the acceleration plates. All right, well, the mass of the electron, I should use blue. I like blue better. Mass of the electron is 9.1 times 10 to the power of negative 31. No, I'm writing this just to two significant figures. If you find it somewhere else in a page of constants, you use whatever significant figures are appropriate for the equation sheet or whatever that you're working with. I'm just using 2 sig figs for simplicity. Minus 1.60 times 10 to the power of negative 19 coulombs is the charge. delta V, that's the voltage, not speed, is 3.00 times 10 to the power of 4 volts. And V1 with an arrow over top, just to remind us that it is speed, is 0 meters per second. That's our values. What we said was negative delta VQ equals the change in kinetic energy. And without using a pre-made formula, that means 1/2 mv2 squared minus 1/2 mv1 squared. Well, if the V1 is equal to 0, remember that formula that we derived earlier isn't on the equation sheet. So if I can get to this stage, V1 is equal to 0. 0. That's gone. This reminds me of like good old-fashioned roller coaster problems. Wow, what a tangled web we weave when first we... Never mind. All right. So we're trying to find V2. So we got to get that V2 all by itself. And you know what? I'm just going to do all of it in my head because I feel like we got to do like 3 algebraic operations all at once. I don't want to waste time. So V2 is going to be equal to negative 2 times delta V Q over M, all square rooted. That's rearranging to get V2, the speed, final speed, the exit speed. And going back to our diagram, we're trying to figure out how fast this thing shot out of the acceleration plates, because really what we want to know is what the x velocity of this particle is when it enters what we're calling the deflection plates, right? Those horizontal plates. This is like Millikan and projectiles all at once. Sub in our values. The exit speed from the acceleration plates, negative 2 times 3.00 times 10 to the power of 4 volts times negative 1.60 times 10 to the power of negative 19 coulombs, all divided by 9.1 times 10 to the power of negative 31 kilograms, all rooted. And I get an exit speed of 1.0271 times 10 to the power of 8 meters per second, or approximately 1.0 times 10 to the power of 8 meters per second. Now, have we broken any laws of physics here? When I say that, why am I asking that question? Yeah, did we go faster than the speed of light? We did not. We did get up to 30% of the speed of light, though. That's how I know this must be a lab grade cathode ray tube. This is not one that I have in my my home, okay? This is a kick butt TV or something used for particle investigation, right? So it's about 1/3 C, because the speed of light is 3 times 10 to the power of 8 meters per second. So this is fast. That is fast. Now, as a side note, quick little side note, I've solved this in a certain way. I want to point out that there is another way that you might see somebody try to figure this out. We know that work is equal to force times distance. Now remember, it's force times distance, but the distance that this electron is traveling from one plate to another, we're actually calling the change in its R value, that the distance across the gap, right? So that's force times distance, the gap distance, that delta R. And we also know that force on that charge is going to be equal to epsilon times Q. So if I call this guy equation 1 and I call this guy equation 2 and I sub 2 into 1, you end up getting the equation that the amount of work done on that electron is equal to epsilon times the charge of the electron times the size of the gap between the two plates. Which means that another way to approach this would have been using this line of thinking, that the change in kinetic energy on that electron is going to be equal to epsilon Q delta R, where delta R is the size of the gap, the size of the separation between the two metal plates. So I actually think that this approach is really kind of cute, and I think it's really useful. So I'm putting it there as a way to also figure out the kinetic energy. And the reason that I would come at it from two different perspectives is that sometimes you know the voltage and sometimes you know the electric field intensity, and you want to be able to roll with your givens, right? So this is a helpful alternative. I just don't want to do like a whole extra example using this alternate method, okay?